Hello and welcome back to Mr. Latham's AQA revision sessions. So, in this video we're going to be talking about P2.4, which is current electricity, and this is part 2. So, carrying on from where we left off, the next part we're going to look at is something called Ohm's law. And Ohm's law, as you can see in the box, states that the current is directly proportional to the potential difference as long as the temperature remains constant. So if we have a look over here at a potential difference current graph for an ohmic conductor, so something that obeys Ohm's law, we see that the line looks like this. So it is a directly proportional graph because it is a straight line that goes through the origin. Okay, and as we increase the potential difference, the current increases, and it increases by the same amount each time. So this is a conductor which obeys Ohm's law. Now, when we're talking about the potential difference increasing, as the potential difference increases, the current increases, we can also say that for an ohmic conductor, its resistance is the same. Okay, so its resistance doesn't change. And we know this because if we look at resistance from our equation on the last video, it is potential difference divided by current. In other words, it is the reciprocal of the gradient. In other words, 1 over the gradient. And since the gradient of this line isn't changing, its resistance isn't changing, so its resistance is always the same, as long as the temperature remains constant. Now, for your exam, there are a number of other potential different current graphs that you need to remember, and the first one is a filament bulb. You can see a filament bulb, or a lamp, has an interesting shape, and straight away we can see it is not an ohmic conductor, because it's not a straight line, it's a curve. And if we have a look even closer, we can see that as the potential difference increases, or as the current increases, the resistance increases. Now, the reason why the resistance increases is because of the fact that the bulb gets hot, or the filament gets hot. As current flows through the very thin piece of wire, the wire gets hot, and therefore it doesn't obey Ohm's law because the temperature is changing. So our next one is a diode, and a diode has an equally peculiar shape. We can see that it has two parts to this. So in the forward direction, we can see that as the potential difference increases, the resistance decreases because the gradient gets steeper and steeper. Okay. However, in the reverse direction, as the potential difference increases, the current remains very low. In other words, in the reverse direction, there is a very high resistance. Hence, that diodes only allow current to flow in one direction. And this is because in the reverse direction they have such a high resistance. Okay, then, so our next one is a thermistor. Now, don't forget, a thermistor is a resistor that is sensitive to temperature. Now, I'll put on here two lines, and the reason I've put two lines on there is because you need to understand that the resistance of a thermistor changes with temperature. So the red line represents high temperature, and the blue line represents a low temperature, so cool and hot. So as you can see, as the temperature of a thermistor increases, its resistance decreases because the gradient of the line gets steeper. Equally, for an LDR, a light dependent resistor, we have a similar type of graph. However, this time the gradient of the line, or the resistance of the resistor, is altered by the light intensity. So the yellow line on here represents bright light, whereas the black line or the grey line represents dim light, or low light intensity, high light intensity. So therefore, as the light intensity of an LDR increases, then its resistance decreases. Okay, so those are the four graphs, the four potential difference current graphs that you need to remember for your exam. So, how do we actually get those graphs? So, how do we produce those potential difference current graphs? In other words, how do we calculate the resistance of a component? And this is a question that they may well ask you in your exam. So, I have an example here that we're going to work through. So, the question says, describe how you could take readings necessary to determine the resistance of a resistor, in this case resistor R. Now, before we can work the resistance of the resistor, we do need to add some components. So the first thing we're going to need to include are a variable resistor, and this is to alter the current. We're going to need a switch so we can start and stop the current, so that we don't have the resistor overheating, because obviously if there's a lot of current flowing through the resistor over a period of time, it will get hot and therefore it won't obey Ohm's law. Therefore we won't have a straight line, so we won't be able to calculate its resistance. And then finally we have an ammeter, which is also wired in series, and the ammeter is there to measure the current that is flowing through the resistor. So I'll just add those to the diagram. You can see, there we go. We have our switch, we have our variable resistor, and we have our ammeter. Now the next thing we need to do, if we want to calculate the resistance, is we need a voltmeter. However, a voltmeter, if you remember back, has to be wired in parallel. Okay, and this is because it needs to measure the potential difference from one side of the component to the other side of the component. So we would wire that in just like that. Okay, so this voltmeter will measure the potential difference from this side to this side. Okay, so what do we do next? Well, then we simply need to record our current and potential difference using our ammeter and voltmeter. We then need to alter the current using the variable resistor, so by altering that. By altering the variable resistor, we will alter the current flowing through the resistor and therefore alter the potential difference. We then continue to do this, recording the potential difference in current at different intervals as we keep changing the variable resistor. And then finally we would plot this as a graph, as a VI graph, and then we could use the gradient of the line to calculate the resistance. In other words, we would do 1 over the gradient to calculate the resistance. Okay, or use the equation R equals V over I. Okay then, so let's look a little bit more about series circuits and parallel circuits, because these are quite often exam questions that you could get asked, and you do need to know the basics of series and parallel circuits and their properties if you have any chance of being able to answer these questions. So we'll start off by series circuits, and I'll quickly whiz through the properties of a series circuit. So a series circuit is a circuit where all of the components are wired in one loop. There is only one path for the electrons to flow. So first off, the potential difference of the cells in series is the sum of the potential of each cell. So if we have the example of 3 volts, so we have 2 cells there, each of them having 3 volts, then the combined potential difference would be simply 6 volts, so 3 volts plus 3 volts. Okay then, so our next one, the total potential difference of a circuit is shared between the components. So in this case we have 2 components, eeny and meeny, and these 2 identical components, in this case bulbs, will have the potential difference shared across them. So since there are 6 volts in the supply, each of these bulbs would receive 3 volts, and therefore the combined across both of them would be 6 volts. Our next one, the same current flows through every component. Very important point. So if we think of this as like a hot water system, and the water flows through the pipe all the way down here, all the way through and all the way back, then the same amount of water flows through this point as flows through this point and this point and this point and this point, and obviously this point over here. So if we say that we have 1.5 amps of current here, then we will also have 1.5 amps of current there. Okay, and our last point is that the total resistance of the circuit is the sum of the resistance of each component. In other words, it means that if we add up the resistance of each of these components, we will calculate the resistance of the entire circuit. So how do we calculate resistance? Well, if we go to our formula sheet, in this case we go to our formula triangle and we put our cursor over resistance, it is potential difference divided by current. So the potential difference here for this one is 3, and its current is 1.5. So 3 divided by 1.5. Equally for this one, again, potential difference of 3 and the current of 1.5. Therefore, the resistance of each of these is 2 ohms. So the resistance of the entire circuit, since there are only 2 components there, would be 2 ohms plus 2 ohms. So therefore, 4 ohms would be the total resistance of this circuit. Okay, so let's now have a look at a type of question they may ask you. So here we have a series circuit. We have a supply at the top of 16 volts. We have an ammeter, which we can see has a current of 4 amps. And we then have 3 fixed resistors, which are also wired in series. And then we have 3 voltmeters, which are there to measure the potential difference across each. So our first question, then calculate the potential difference across resistor 1. So we go to our formula triangle and we want to calculate the potential difference. So I put my cursor over V, so you can see to calculate the potential difference it is current multiplied by resistance. Now since the current's the same through all of them, we know our current is 4. And we also know that its resistance for resistor 1 is 1.5 ohms. So for resistor 1 we simply multiply our current by our resistance. So current of 4 multiplied by a resistance of 1.5. Therefore the potential difference we would measure here would be 6 volts. Okay, let's do the same for resistor 2. So we have a current of 4 and a resistance of 2. Therefore we would have 4 multiplied by 2, which means that resistor 2 would have a potential difference of 8. And then finally for 3 we would have a potential difference of, well, we need to calculate it. Now this one is a little bit tricky because it doesn't give us the resistance over here. Okay, so we're a little bit stuck here. However, what we do know is that the total resistance of the circuit is the sum of these 3 components. And since we know that the supply here is 16 volts and we have over here 6 volts, we have over here 8 volts, we therefore know that this must be 16 volts take away the potential difference of these 2 which we've just calculated. So our potential difference across resistor 3 would be 16 take away 6 take away 8 gives us 2 volts. So now we have the current of 4 which is flowing through all of the components, and we have the potential difference across resistor 3 of 2 volts. So now we can proceed to calculate the resistance of the potential difference of in fact, what am I talking about? We've actually now calculated it. So because we have 6 volts there, 8 volts there, 6 plus 8 plus 2 equals 16. So I went a bit off plot there. I forgot what I was calculating. Anyway, calculate the resistance of resistor 3. So how do we calculate the resistance of this? Well, let's go back to our formula triangle. We put our cursor over resistance. To calculate resistance we have potential difference divided by current. And the potential difference, we've just calculated it. It was 2. And we know that the current flowing through it is 4. Okay, so our resistance would be potential difference 2 divided by current of 4. Therefore our answer would be 0.5 ohms. Okay, so I did the potential difference of 2, which I calculated here, divided by the current. Okay, then so number 3 then, what is the total resistance of all 3 resistors? Now if you remember back to the last slide, we said that the total resistance of a circuit when all the components are wired in series is the sum of all of the resistances. So for this part, quite straightforward, we just simply need to add up the resistance of each resistor. So we have 1.5 plus 2 plus the resistance we've just calculated of 0.5. So we add all those together and it gives us a total resistance of 4 ohms. So that was just 1.5 plus 2 plus 0.5. Okay then, so parallel circuits. Now parallel circuits are almost like the opposite of series circuits with regards to their properties. So start off with, if we have a supply, again we have 2 cells. These 2 cells each have a potential difference of 3 volts. Therefore combined we would have a potential difference of 6 volts. So the potential difference is the same across all of the components in the circuit. So this is the first property. Totally different, the opposite in fact, of what we have with a series circuit. So since we have a 6 volt supply up here from our two 3 volt cells, the potential difference across each of these would be the same as the supply. In other words, both of these cells would receive 6 volts. Okay. Right then, our next one then is the current of the whole circuit is the sum of the current through the separate components. In other words, it means that the current splits. So this is the opposite to series circuits. In series circuit, the current was the same all the way through, but the potential difference was split, whereas in a parallel circuit, the potential difference stays the same. It's the same as the supply, but the current splits. So if we just pick some values, so we start off here with 2 amps of current here. Once it reaches this point here, then there is 2 paths that the electrons can take. So what happens is some of the electrons travel down this wire and some of the electrons travel down this wire. Now in this example, just to keep things simple, I've said that 1 amp flows through this wire. Since 1 amp flows through this wire and 2 amps went in, then 1 amp must flow through this wire. Since we have 1 amp flowing through here and we have 1 amp flowing through here, once they get to here, those 2 currents will combine. So therefore, flowing back up this wire, we would have a current of 2. Okay, so then the two 1 amps come back together to make a current of 2 amps. Okay then, so let's have a look at a question that they may ask you in your exam. So we've got here calculations on parallel circuits. So you can see here that we have 3 resistors. Now this time these resistors are wired in parallel because each component is wired in a different loop, and there is different the electrons can take different routes through the components. So number 1, calculate the current flowing through resistor 1. So we'll go to our formula triangle again, and we're looking for the current, so we're looking for I. So if I put my cursor over I, you can see to calculate the current, it is potential difference divided by resistance. So what is the potential difference? Well, we've just said on the last slide that the potential difference is the same across each component as it is from the supply. In other words, there are 6 volts of potential difference across each of these components. And each component, each of these fixed resistors, we can see we've already been given the resistance. Therefore, to calculate the current, it is the potential difference divided by the resistance. So for our first one, it would be potential difference of 6 divided by a resistance of 1, which would give us a current of 6 amps. For our second one, we would have once again 6 volts across this component divided by a resistance of 2, which would give us 3 amps. And then finally for our last one, we would have 6 volts divided by 6 ohms, which gives us a current of 1 amp. So then finally, what is the current flowing through the resistor shown on the diagram? So what is the current flowing through this one? Now if we just go back to our answers for this, you can see that we have 6 amps flowing through here, we have 3 amps flowing through there, and we have 1 amp flowing through there. Therefore, if we combine them, we have 1 and 3 and 6. Therefore, the current flowing through here, equally the current that must be flowing through here, must be 6 amps plus 3 amps plus 1 amp. In other words, 10 amps is our total current. Okay then, so let's finish off then with a trickier question. Now this is actually a compound circuit where we have both series and parallel. Now this is, as I said, one of the most difficult questions you could get at, but if we stick with the ideas we've just been looking at with series and parallel circuits, it is possible, it is logical to be able to calculate these answers. So let's start off then. So we have here the diagram above shows 3 fixed resistors wired up to 3 3-volt cells. So up there we have 3 3-volt cells. So therefore, before I do anything else, I'm going to work out what the total potential difference of this circuit is. And since we've got 3 3-volt cells, we must have a combined potential difference of 9 volts. Okay, just done 3 plus 3 plus 3. Okay then, so what is the current through resistor B? So what do I need to identify first? Well, we have a supply of 9 volts, and you can see that there is a potential difference across this one, this resistor which is in series, of 3 volts. Now, since there's 3 volts travelling through this one, there must be across these two a potential difference of 6 volts, because 9 volts take away 3 volts is 6 volts, and since these are both in parallel, they must both be receiving the 6 volts that's left over. So 6 volts across this one, 6 volts across that one, and then the 3 volts there. So the 6 plus the 3 gives us 9 of the supply. So what is the current through resistor B? So we can see resistor B, we've just worked out that it has a potential difference of 6 and it has a resistance of 3. So what is the current? Well, we put our cursor over the current, so it is potential difference divided by resistance. So potential difference divided by resistance. The potential difference we've already worked out was 6. Since 3 is there, there's 6 left over here. So it is 6 divided by its resistance of 3, which gives us 2 amps. Okay then, so what about for resistor C? Well, it's the same process. Again, we use potential difference divided by resistance. The potential difference is 6 because it's the same as it is for through this one, because these two are wired in parallel, and it has a resistance of 4. So our current flowing through resistor C would be 6 volts divided by 4 ohms, which gives us a current of 1.5 amps. So, to finish off, what is the resistance of resistor A? Right, so this one's a little bit trickier. So to work out the resistance, if I just put my cursor over that, we need the potential difference and we need to know the current. Now we know what the potential difference is because it says here it's 3 volts, yet we don't know the current. However, if we go back to the parallel circuit part of it here, we know that as the current flows through here, the current splits. Some of it goes down here and some of it goes up there. And in fact, we have just calculated from the last 2 questions how much current is flowing through each. So we have 2 amps flowing through there, and we have 1.5 amps flowing through there. So then at this point, when those 2 currents come back together, we must have flowing through this wire, and therefore flowing through the resistor A current of 2 plus 1.5. In other words, the current is 3.5 amps flowing through A. So now we have our current and now we have our potential difference, we can now calculate our resistance. So our resistance is potential difference divided by current. So potential difference of 3 divided by the current which we've just calculated of 3.5. And that gives us an answer of 0.86 ohms to 2 significant figures. Okay? So as I said, this is the most difficult type of question you may get asked. I would probably, I don't really want to commit, but I would say that it is unlikely that they would give you a question this difficult. However, you can see that as long as you remember the rules of series circuits and parallel circuits, it is actually quite logical to be able to calculate this. Okay, thank you very much for listening.